Yes, recording is in progress, so I can start now. The title was set. The outline is I first of all will show you the motivation about my job, about my research that I doing. Then I briefly present parallel programming, different languages, different tools that can help you to write parallel programs, and then move to the description of the PCJ library. And at the end, the applications and some benchmarks on that. I have multiple slides, but I think that I could skip some of them and to not take too much time. But if you have some questions, then I can move back or answer some questions. And that probably that first slide with outline could be a good illustration what um, uh, what uh, what is parallel programming, because I from the sequential processing we can try to create applications that could parallel process some data that could finish earlier. So the first is motivation. Uh, there is some empirical or law that's called Moore law. Uh, that law states that the number of transistors on a microchip doubles about every 2 years. At the beginning, it was said that it's about 1 year to double the transistors on a microchip, and that was said by the co-founder of the Intel. You probably know the Intel company that creates processors, and he not only states that what he see, but also wanted to tell uh, his employees that they have to work to double the to find a way to double the number of transistors on a microchip. That Moore law has been extended to other computer parameters like speed, but because the maximum clock speed of processor is steady from about 2005. Um, um, because there is problems with physical laws that and the heat and the problems in too little scale. But the number of transistors increase, but it's not because of increasing speed of the single processor, but because of the number of computational units increase uh, in one unit. Okay, uh, we are in the Damsi Center, so some we can do some exercises, mathematical exercises, and I show that slide to the students at the beginning of the lecture about parallel programming. And I will show you also here. Maybe you could try to answer that. And there's a slide about motivation. So exercises. Uh, a worker can dig 2 meters of ditch in 1 hour, and in what time he will dig a 20 meters ditch. Normally, students are very shy and don't want to answer to that question. Maybe they think that it's too hard for them. I don't know. Maybe you know what is the time? Somebody? Okay, I assume that the worker is not being tired, so um, the time is 10 hours because 2 meters per hour and 20 meters. So it's 10 hours to complete a ditch. And now, in what time will 10 workers complete this ditch? 20 meters ditch.
Napisz opinię dowódcy medoterapii
Camila,
głowy.
you
Przepraszam.
have okay.
Sorry.
Okay, uh, so um, 10 workers can complete that ditch in 1 hour because here also I'm assuming that the workers will not interrupt themselves. Okay, and next slide is again about digging, but now a worker dig well, 1 meter of well in 4 hours, and in what time uh, will he dig a 5 meter well? And we can calculate that is 20 hours. And then a little harder question. In what time will 10 workers make this well? And as we can see in that in the photo, the well is not big. Only one person can be inside. So that 10 workers, we cannot assume that 10 workers can dig at the same time. So it depends. In answer to that question depends on the work that each worker is doing. They cannot just dig in the same time, but because they would interrupt themselves, that only one worker probably could dig, but we could think about one worker will do something, what the other will take the bucket with what is digged, and so on and so on. So that is the motivation about why parallel programming is important, because some works are easy to parallelize, like digging a ditch. Other are not so easy, like digging a well. And um, we have in our computers multiple cores that process data, and if we would like to have some uh, computation done faster, so we should probably divide that problem into the pieces, that workers that could work in the same way, doing all exactly the same things, and other workers that can help to do to finish some computations in earlier, but doing other things. That's also some illustration of problem division for parallel computing. Okay, second motivation, why Java? Why I'm using Java for my research. It is some personal things, but from the more concrete things, it's the Java that has multi-threading in mind from the beginning, from the version 1.0, because it has Java lang thread class in the standard library from the beginning. And what's more, the Java lang thread means that the class thread is automatically loaded in the context of the application um, 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 from the beginning of the execution. So the thread is um, we can use threads without importing any class. It's built in, and it's very important for the Java. And Java then in next versions uh, have received some classes, some frameworks um, that could um, help to parallelize computations, like package Java util concurrent that contains multiple classes for uh, uh, use uh, to use them uh, in parallel com concurrent computations. That was in Java 5. Java 5 also introduced new Java language, Java memory model. So it was very important version of Java. And currently, Java 2021 introduced virtual threads that could also help to write a very easily the parallel constructs in Java. Moreover, there are plenty of applications and frameworks that are based on Java and Java Virtual Machine. You probably hear about Apache Hadoop, Apache Spark, and maybe no Akka library. And why all else the Java is important? Because it's one of the most popular programming language. Uh, there, in the TOP index, there is Python, C, C++, and Java in the top places of the ranking. So Java is still very important. Okay, so that was some slides about motivations. Now I will present parallel programming very briefly. How parallel programming is done. Of course, there are some low-level constructs in the systems, like threads, that pit thread, POSIX threads that can be used, but that that POSIX threads are hard to use. Mm, and there are some um, libraries, some tools that can be used to help to write parallel programs. And one of them is OpenMP. OpenMP is for C, C++, and Fortran. For that language it's written standard, and it has more than 25 years now, and it's currently in development. In last year, the 6.0 version was released. OpenMP works in environment with shared memory. So when the CPUs, processors, cores has access directly to the memory, and it gives very uh, uh, easy to use constructs to uh, to to, to show parallels to write parallelize concurrent programs. So we could use some compilator directives, and then the application can run using multiple threads. In the other standard of writing parallel codes, especially in multi-node environment like clusters, is MPI, message passing interface. It's much older than OpenMP because the first version was presented in 1992. So it has more than 30 years. And the standard in version 5 was released in current year. Standard presents the structures for the C and Fortran languages, but some other languages like C++, Java, Python have some wrappers, some bindings to use the MPI libraries. As I said, the message passing interface is for the multi-node environment concurrent programming. So each CPU has access to its own memory, and if we would like to send some data from one node, one computer to another, we have to write some code like MPI send on the one node that will send the data, and on the other MPI receive to receive data that was sent by other node. Currently, if you have multiple nodes with multiple cores on the clusters, there are solutions that mix the MPI and OpenMP computation to utilize the nodes effectively. But it's a hybrid solution, and it's harder to write that programs. In the Java, there are also multiple work to research programs that try to provide multi-node processing on using Java. There was some distributed JVMs that could be seen by the applications like one big JVM, but that was done in many years ago, and it wasn't so performant like other solutions. There was some dialect of the Java called Titanium that tried to introduce some parallel constructs into the library, but it was Java 1.4, and there are many changes in the Java language that Titanium was not adopted for the next version of the Java language. And what is more important here, that the Titanium translates the Java language to the C and then compiles C code. So the Java virtual machine with garbage collector and other stuff was not used at all. But the only thing was the similar um, um, syntax of the language was used. And there are some RMI solutions, remote method invocation, and that works. There is proactive library that used that RMI um, for parallelism, but the overhead was big for that computations. MPI Java, I said earlier, some Hazelcast and other libraries like PGAS, Akka, Hadoop, and Spark. You already heard something about that. Hadoop is based on the Google file system from 2003, so it it has 20 years now. First public version was released in December 2011. So it's much younger than OpenMP and MPI. Uh, and the most important thing to know about Hadoop is that it is using a MapReduce model to process data. So at the beginning of the computation, there is reading data from the input, then mapping, so transforming that data into other form, filtering, shuffling, and then reducing the mapped values to one smaller, and then saving that to the disk. Next, Spark. Spark also use MapReduce model, but instead of reading data from disk and saving data to disk, it used resilient distributed dataset. So it's not necessary to save immediate steps to the hard drives. It's uh, um, uh, it is that is something that provides more performant computations. Uh, and Spark works also using Java Virtual Machine, and there are interfaces for the Scala language, Python, Java, and R. Another, maybe not language, but the library, another library is Akka, that is based on the actor model to process data. Parallelism is based on the transmission of the messages. The stored data is immutable. There is no syncing. Actors work transparently. Uh, and if we would like for the actor to do something, we have to tell them to do some computation to change its internal state and so on. It's a different um, model of processing. Uh, s- different Other different model is PGAS, Partitioned Global Address Space, and um, it is more similar to MPI and OpenMP, maybe is more close to OpenMP, because we have shared memory space, partitional address space memory that looks like or try to look like it's shared memory across all the nodes, but uh, that memory is attached to the nodes. So if we would like to get some data or send some data, we have to directly use some network to access that data. But we don't have to ask other mm, partner, other peer to send data to us, but we can just ask send me a request and that request um, give us that data. So we have independent threads, we have local and shared variables, uh, and the global variables are visible to all threads. The important thing there is we have one-sided communication, and that communication is hidden to programmer. The PGAS programming model, PGAS paradigm, is implemented in the PCJ library. Uh, that, uh, that library was created and developed as part of my doctoral dissertation. And the main principles are similar to that PGAS paradigm. So it has local and shared variables. Uh, Shared variables are available from all threads. There is one-sided communication. Peer peer don't have to give special access to the data. Communication is done by invoking appropriate methods, and there is some more technical thing like possibility to register multiple shard space, but I will skip that. The PCJ library is based on Java 8, but works on all systems with Java 8 and above. So it works up to the newest versions of the library. It doesn't require any additional libraries, so there is no problem with dependencies, and doesn't need special infrastructure. I can develop applications in using PGAS library on my own laptop, on some workstations. I can run that code on computing clusters, supercomputers, and even clouds. The library is open source. It has a BSD license. It's available at GitHub, and the binary version is also available from the Maven Central Repository. The library um, received the HPC Challenge Award at the Supercomputing Conference 10 years ago. By presenting effective way of programming parallel applications. That award was teamwork of Piotr Bała team. That slide presents the almost all important classes and methods that are enough to write parallel programs. We have some execution builder to create new parallel execution, and we have the PCJ class with methods that could give us the ID of current threads, the number of threads, getting and putting data in asynchronous way, or one-sided or just one-sided in blocking manner, and other like collecting, reducing, doing some barrier splitting groups for creating new subtasks, and so on. So that slide shows everything that you have to know to write parallel programs. That's the only constructs that are needed. Uh, we as a team published the tutorial paper. We have been invited to present to give the tutorial at some conference, and publish that paper that shows that um, how to use the library. Mhm. Okay. PowerPoint stopped. Uh, Stopped now. I'm not sure why, but I have to. Okay. Okay. Probably I have some technical problems. I hope that everything will be fine. Okay. That's the schema of how that calculations works. We have two physical nodes. On each physical node, there is a Java virtual machine that runs our computation, our application, and we have shared variables, we have some local variables, and we can read data from our shared variables to the local variables, or put our data from local variable to shared, or uh, uh, take uh, data from shared variable of other node to current to current node, and on each JVM there is multiple PCJ threads that do some computations. Mm. Hmm? I have to. The, I cannot switch the slides. Maybe I have to close the PowerPoint. And open again. Hmm? Okay. I hope that now we, we have that slides. Um, if we use that communication inside JVM, we use some local workers to transfer data, because the data in Java is the objects are given by the reference. If we would like to have copy of data, we have to do some clones, but normally clone methods create a shallow copy of the data, so the deep copy is needed, and to do so we use some marshalling, uh, um, serializing and deserializing the objects. Uh, if we use the network, that mechanism is natural, because to send data through the network, we have to serialize data somehow, and then deserialize on the other side. I have some technical issues. Maybe I will. So, and now some applications. Uh, some applications are mm, written by me, some by other people in the team, some by other people, and um, here we have Java ray tracing using some code from Java Grande from benchmark. That code was prepared for MPI, and I have translated it into the uh, PCJ execution. The Conway's game of life, maybe you know, um, that is simple to the two-dimensional stencil, where the uh, each cell is alive when it has uh, two or three survive to the next generation if that cell has two or three neighbors, and the cell can be born when that cell has exactly three neighbors that are alive. So that's two applications. Two other applications, the finding parameters of the neural network simulating connectome of C. elegans, is a doctoral dissertation of Łukasz Górski that he used the PCJ library for that computation. The dissertation is much has more algorithms, but from my perspective, the most interesting one is that C. elegans. Another dissertation, doctoral dissertation by Magdalena Ryczkowska is about the graph problems implemented in the PCJ library. Here we have example of traversing of a large sparse graph that imitates the really scale-free network with small diameter. That both doctoral dissertations were successfully finished in 2017 and 2018. And other applications that are the result of the hackathons at the ICM University of Warsaw Grand Programming Challenge hackathon. First hackathon mapped the gap. The problem was to design the fiber optic network development in Poland, and the students create a solution that uses the PCJ library for the uh, for finding that where that network should be placed to give the most wide access to the fiber optic network in Poland. And another hackathon was the called Smart Church, was to design the network of electric car charging stations in Poland. So taking in account the density of the people in some areas where that charging stations should be placed, and that solution was also created using the PCJ library, and that the solution was created in 24 hours of the hackathon. Other applications was word counts, that the showcase of the MapReduce model from the Hadoop, but we also implemented word count in application in the PCJ library. Our team evaluated that word count using the weak scaling technique on some clusters, and presented results and compared the performance with the Hadoop. And we can see that the PCJ is running much faster than Hadoop. The Hadoop cluster was consists of 68 servers, computing nodes, 3 name nodes, and 2 management nodes. And all computation was done on that special Hadoop cluster, and on the same cluster we execute the PCJ to do our calculations. The lower values means better performance. So the PCJ is much better, but we have to take in mind that the file is very small. It's only 10 megabytes. Maybe we used 16,000 of input files that we read, but that is only 10 megabytes. And that was created by our team. Another application is the PCJ Blast application that is used for searching the similar DNA sequences in the genome database. And it read the reference database. It uses NCBI Blast application to do essential computations, but PCJ was used to parallel to run that application in parallel way to speed up computations. There is on the bottom of the slide the sample FASTA file is presented here. To speed up everything, we cannot just divide the input sequence file into the equal pieces, because some sequences are processed in 5 minutes, in 7 minutes, but all other in the few minutes. So it has to be dynamic. The dynamic load balancing was important here to provide the best performance. That is the schema of the calculations. The sequences are read by the one thread called scatterer, and that thread gives the sequences to process by worker threads that use NCBI Blast with threads to process data. Then that output data can be further processed, and then the output is saved to the output files. Okay, that application give possibility to process input file that in normal situation would be processed in 56 days, and that computation time using 64 nodes was decreased to one day and 1 hour. Other application that is TerraSort, so implementation of some sorting algorithm. It is generalization of the quicksort algorithm that uses p-1 pivots, splitters, instead of one in the quicksort. And in that paper, I have compared performance of the Hadoop TerraSort that won some time ago the TerraSort challenge with the PCJ implementation of the same algorithm. And we that two charts shows the different approaches to access data. First is external mode, where the data is not placed on the same node as computing node, so the data has to be transferred from the data node to computing nodes. And in that situation, Hadoop is the empty inside um, uh, uh, icons is much worse than the PCJ that is filled one. Um, but it's not natural way of doing computation in Hadoop. So uh, the other benchmark was to check how Hadoop will um, be what will be the performance when Hadoop compute nodes are on the same nodes like data nodes, and then that is much better. Um, because for the lower number of threads uh, that the Hadoop version was more performant, but for the greater that difference was not too much. And but still uh, the gap between the Hadoop and PCJ don't give me stable mind. Uh, I checked the configuration of Hadoop and saw that the there is uh, that I can change the memory maximum memory used by the mapper and reducer. I have again problems with presenting. I'm not sure why. Okay. Uh, I can change that value, and when I set it to 5 GB, 10 GB, 20 GB, and 40 GB, I saw that the most performant was when I set that memory to 10 and 20, so I selected 10 GB as it gives better performance for the biggest files processed. And that are the results. And in that results, maybe on that I can use my pointer. On that results for the 10 to 10 to 10th records, the Hadoop is more performant for the lower number of threads, and for the 64 threads, the performance of the PCJ and Hadoop is similar. For other, the um, depending on the configuration of the PCJ, it's also all the performance is the same or uh, worse. But I will skip that because I see that it's 11 then. To show you other applications. Other application is the possibility to run PCJ on on the cloud. PCJ was created with clusters and supercomputers in mind, where each node is running at the beginning. The cluster system uh, um, give access to that to the nodes. Each node is connected somehow with each other, and that is stable. Everything is stable. In cloud, the instances are independent. They can run in uh, in collaborative way, but it has to be configured properly. And I um, sh- uh, show here with Łukasz Górski and Piotr Bała that it is possible to run PCJ on cloud, even on clouds. Moreover, clouds give us access to the ARM processors, and we could benchmark not only Intel processors that are on the supercomputers and clusters, but also ARM processors that are available from the Amazon Web Services Elastic Cloud, Elastic Compute Cloud, and Linaro Developer Cloud. That slide presents how to configure everything. But I will skip that because it's the slide um, that image is from the paper presented here, performance evaluation of Java PCJ implementation, parallel algorithms on the cloud, and if somebody is interested, it's possible to find that and read it. Uh, the, there are some applications that are used for the benchmarking. Here is the desk decryption. This is very CPU intensive application that can be trivially that is trivially parallel problem, and the implementation is based on analysis of all possible encryption keys. The in benchmark, all keys are generated to cover all possible combinations of given key length um, to check the performance, and whole range of keys are tested. Uh, and as you can see here, uh, uh, we could be able to run that application on the cloud, on two different clouds, Linaro Cloud and AWS, and also on the Cray XC40, so the supercomputer, but with Singularity, so some virtualization mechanisms like that one used in the clouds. Other application is fast Fourier transform. You probably know that algorithm. That algorithm computes the discrete Fourier transform. Our implementation is based on the algorithm created for the co-array Fortran. That is the solution implementing the PGAS paradigm. And one thing more to set here, the same Jai library that contains that compiled version of the application was used for the Cray, for the AWS, and for the Linaro clouds. So this I compile file only once and copy it to different systems, and in using that single library, single jar file, that computation was created. So I write the code only once and use compiled version, the same compiled version on different machine, and it works. Word count I presented earlier is another application that we run on cloud and show that the performance is very good. Uh, and what is interesting here, uh, the linear clouds instances of on the linear are all instances are the ARM processors, but that that M1 small performs much better than other because it's the ARM processor that that is built by Qualcomm, and that uh, other are the Cavium Thunder. The processor clock speed is not is not much slower, but for all the results that Qualcomm Falcor is gives better performance than that Kavit. Uh, and all having that we know that we could use PCJ on the cloud. We also test how is it possible to write data and artificial intelligence applications using the PCJ library. Big data is you see that word count. It's some showcase of the big data processing. For the artificial intelligence, you heard about neural networks, so modeling the connectum of C. elegans, and but we also checked the possibility to use distributed neural network training. Hmm. Game of Life, we were able to run on a very large supercomputer called Hazelhen, and we were able to run that um, uh, that application using 4,000 nodes. That means about uh, 200,000 of threads on that Hazelhen supercomputer. Uh, and it that the application uh, was scale very well up to the 2,000 of nodes. So in that time the Hazelhen was seventh or ninth in the 19 about in first top 20 of the top 500 lists. So it's in the top of the supercomputers at that time when the data was collected. Uh, Word count we compared with another library that can be used for PGAS programming in Java, PGAS, and uh, we could use that for the um, also for the computations, and uh, the evolution algorithm, and that distributed neural network training using the Horovod and on the NIST dataset. Okay, I will skip that. Next thing is that some applications use some especially FFT use some all-to-all reduction, and mm, at the beginning the library doesn't allow doesn't have any constructs that could easily write that all-to-all reduction scheme. So in the next versions, that uh, some collective operations has been added to the library, like reduce in version 5.1, collect, scatter in 5.2, and uh, uh, and there's some optimization of processing data. Prior version 5.2, the requester sends request to use collective operation to node 0. Node 0 started the communication, and that communication tree was um, the same always. So even if thread 0, thread 9, thread on node 11 wanted to do some collective operations, it used the same communication tree. In version 5.2, we introduced the shifting of the tree. So the requester becomes the root of the tree, and other nodes are calculated normally, but with that shift. And uh, this gives us the performance gain. Here, blue triangle pointing to up is the Gutter, the FFT using Gutter method in version 5.1. And it gives about 1 gigaflops, 1 gigaflop per second. But with the same code, but with the newest version of the library, uh, there's tenfold better performance. It's about I don't see exactly, but probably 12 gigaflop per second. So only the change of the library, Java library, gives much better performance. For the word count, there is no much performance gain, because the reduce is done only by one thread, so that shifting doesn't help, but it even does not give performance loss. That is good. And last paper, that is HPV kite. The PCJ was used for viral sequence-based detection using camera data and Tversky indexing. We use that HPV kite for rapid scanning of large genome datasets, identify HPV sequences on that dataset, and that probably could be used for any next generation sequence data. The main concept is based on shingling. The reference database consists of 222 HPV viruses from the PAVE database, and we shingle the create numbers from database and from the input sequence, and that input sequence doesn't have to be previously preprocessed. So we have here the time gain, and then we calculate the coverage of the virus in the sample. That give us better performance than currently used applications like Diamond for searching um, viruses in sequence data is sequence data. Moreover, we could use um, eight eight nodes easily um, using our approach. When using diamonds, it's a little more complicated to use more nodes to process data. We have also compared us with the Kraken, and the results are also a little better. About 3 minutes, so it's about 20 20%, if I calculate correctly. We can give results much quicker, but Kraken is used not only for finding concrete viruses, but it shows the more information. But Kraken cannot be easily run on multiple nodes, so there's some trade-offs. Okay, that is everything that I wanted to show you. I think that uh, um, that the presentation shows you that the PCJ library can be used in multiple places, for multiple cases, uh, and the performance is good, and uh, if you have some problems need that has to be processed by computers, especially in parallel way, I'm open to collaboration. Thank you.
Thank you for your talk, and now we have time for some questions.
I have one question. So, do you think maybe that it would be a good idea to make this library accessible also for .NET platform?
So you mean rewrite it in C#?
Something like that.
I try to convince some students that looks they know C# well to write subset of the subset of the library, but no one want to do so. But probably if we could have some doctoral students, the PhD students, they maybe there is some open questions that maybe they could do something like that.
And I'd like to say that the results are really impressive. So congratulations for you.
Thank you.
So, any other questions?
Yes, I have a question.
Mm-hmm.
In a scenario where nodes in network have a vastly different computational capabilities, it's usually hard to optimize asynchronous communication, for example, in order to avoid blocking. Does your library implement, or is it considered to add a runtime that optimizes data flow in order to reduce the communication overhead?
It depends on the problem. So probably the user has to write code that will optimize for that situation. But as far as I remember, we use we did some benchmark on Topola cluster at the ICM, and at the Topola cluster there are multiple different nodes with different processors with different capabilities, and if I remember correctly, it was possible. But that was done some years ago, so I don't remember what was the performance, and if we use mixture of the nodes, or we use only the same type of nodes, even though the Topola has different nodes in its resources. But if you could give more information about the problem, I would try to think about that. Thank you.
Okay, thank you.
Okay, thank you for your questions. Are there any other questions today? If not, so let us thank the speaker for his presentation and his impressive work, and let us finish our seminar. Thank you for your attention.
Thank you.
Thank you. Bye.